morning, everyone. So, today we Team Sheet Metal Forming are back with a new topic, that is thermomechanical study. Cold metal forming and blanking are among the most frequently used mass production process for sheet metal. To meet increasing requirements concerning part quality, cycle times, and service life, this precise process knowledge is essential. During every forming operation, a temperature rise occurs in the workpiece forming zone. The effect has three causes. First, up to 90%, 95% of the plastic work dissipates into heat. Only a small part is stored as dislocations and other lattice defects in the sheet metal. Second, microscopic friction between contact surface, and third, microscopic friction on the atomic level for generates heat, especially during forming operation with high surface pressures and deformation degrees such as embossing or blanking. Temperatures or several hundred degrees can occur. The temperature rise strongly influence the process. Material behavior and tool wear are just two examples. Furthermore, temperature is a decisive factor in the choice of tool coatings and lubricants. Therefore, precise knowledge of the height and profile of the temperature that occurs is indispensable with respect to process parameters. Thank you. Next to Tapas.
Thank you, Danisa. So next, several reports have dealt with the topic across various forming and blanking investigations, but the determined temperature differs significantly even during similar manufacturing processes. Gross et al. Calculated maximum temperatures of 30 degrees Celsius for deep drawing, which is characterized by smaller surface pressure than embossing. Furthermore, when processing aluminum, lower temperature occurs due to the reduced mechanical properties compared to steel. During blanking of steels, authors indicate mostly higher values from 50 degrees Celsius to 600 degrees Celsius and even 1000 degrees Celsius. This discrepancy is mainly due to undefined geometric and temporal resolution of the measurement signal. They confirmed the significant influence of the process parameters on emerging temperature, especially the wide range of measured temperatures shows a high research demand concerning this topic. For that reason, a tool workpiece thermocouple was complemented in a new tool and several embossing examinations under varying process parameters were conducted. Investigations of smaller clearance and faster velocities compared to former examinations have enriched knowledge of temperature and improved undertaking of the sheet metal forming process. So thank you. Over to next.
Thank you. I'm Swapnali and I'm going to speak about the measuring principle. There are several measurement techniques for determining temperatures, but the cramped conditions in a forming tool hamper precise temperature measurement. High surface pressures prevent the use of foil or fine wire thermocouples on punch or sheet metal because of insufficient robustness. Another possibility is the integration of thermocouples in small holes in a punch that weakens the tool. Other methods cannot be used because of limited space. In sum, the challenge is to ensure high quality measurement that is instantaneous and at a defined location without influencing the process. Thermoelectric phenomena offer the possibility of transforming tools to temperature sensors. Based on different thermoelectric properties of sheet metal and tool, these materials can form a thermocouple. Thermoelectric voltages always rise if two different electrical conductors are put together at one end that has a different temperature than the other ends. In this case, the thermoelectric voltage is proportional to the temperature gradient along the conductors. The proportional factor is the Seebeck coefficient, which represent thermoelectric material properties. During cold metal forming or blanking, an electrical contact between punch and sheet metal emerges. The dissipation of conducted plastic forming work and friction between sheet metal and punch result in local heating of the contact area. Subsequently, charge carriers in the conductors reach different energy levels. A thermodiffusion starts. The resulting potential difference changes with the temperature difference between the junctions and can be measured with the voltmeter. As the measurement area is identical to that of the heat generation, an instantaneous measurement of the temperature occurring during every kind of forming process can be guaranteed. Now I want the next member to carry forward the presentation.
So now I am going to tell you about the calibration of the thermocouple. To deduce a temperature from the measured voltage, calibration of the thermocouple is necessary. As the thermoelectric material properties can only be determined experimentally, a special measurement device was used. Its basis is the integral measuring method, which requires a defined temperature gradient along the sample. The electric circuit used for calibration. One end of the sample is heated to a defined temperature T-hot with a maximum of 600 degrees Celsius. The other end is kept at the reference temperature T-ref of 0 degrees Celsius in an ice bath. Both ends are attached to a pure platinum wire, which serves as reference material. Depending upon the Seebeck coefficients of the sample Sb and reference material Sa, a defined thermoelectric voltage. This voltage lies within the range of few millivolts for metals. Therefore, the signal is first amplified and then recorded with a precision voltmeter. The sample is pushed against a block of pure copper by a pneumatic cylinder. To ensure a well-defined and reproducible electric contact, the adjustable force is observed with a piezoelectric sensor. Another key factor is temperature. As the calibration quality directly depends on temperature measurement accuracy, two high-precision thermocouples are placed directly at both junctions. They are small to minimize time delay due to heating. An argon atmosphere prevents measurement errors and because of chemical effects at the sample surface and platinum wires. Characterizing both standardized type K thermocouple lags shows a maximum measurement deviation of the measured thermovoltage of 1.5%. Over to Ankur.
So now I'm here to express about tool and press. Experimental tool that has a 4-pillar structure providing high stiffness and the application of smallest cutting clearances down to 25 micrometer. Due to its modular design, the tool is very variable and suitable for parameter variations. A configuration blank holder force allows analysis to different materials. The punch and sheet metal are electrically insulated from the remaining tool to prevent interfering signals. This is done with the application of zirconium oxide on the die, blank holder, and the punch. The whole tool consists of 4 stations, where both forming and blanking operations can be implemented. A fifth station can be used for cutting sheet metal strips. This enables instantaneous and simultaneous temperature measurement due to, during continuous stroke experiments. The forming forces are measured by piezoelectric load cells in every station and the punch travel by a contact-free eddy current sensor. Over to the next person.
Discuss about investigated materials. To gather information not only of parameters but also of seed material and thickness. The following seed materials were chosen. The austenitic stainless steel 1.4301 has a thickness of both 2.5 and 4 mm. A high tensile strength of up to 720 megapascal and good corrosion resistance make this material suitable for many applications. The hot rolled fine-grained steel S355MC with a thickness of 4 mm is a representative steel for cold forming and blanking operations. Its tensile strength of 491 megapascal is about 32% lower compared to 1.4301. The punch is made of CFH40S, a powder metallurgical cemented carbide. Its fine-grained structure and high homogeneity provides constant thermoelectric properties across the whole punch and thus a high quality temperature measurement. Its hardness of 1400 HP10 allows use for forming and blanking processes. That's all from Team Sheet Metal. Thank you. Please like, share and subscribe our YouTube channel.